Hello, my name is Roberto Trotta and I'm a professor of astrostatistics at Imperial College London and visiting professor of cosmology at Gresham College. Today we're going to talk about the mysteries of the dark cosmos. And as we all know, the cosmos is an infinite source of fascination for many of us. If we look up at the night sky on a dark night, when we have the opportunity to do so perhaps from a dark sky reserve, where we can admire the beauty of the firmament in its entire splendor, we will see thousands of stars. We might be able to see the streak of the Milky Way across the sky. We might be able to see planets. The moon perhaps might come to visit us. And we wonder, what is it that's out there? And if we use a more powerful telescope, like the Hubble Space Telescope, for example, then we will peer even further out in space and even further back in time. And we will see all sorts of magnificent galaxies populating the universe. But actually, one of the major discoveries of modern cosmology is that everything we see in the night sky is just a tiny tip of the iceberg of everything there is. In fact, the universe is much more complicated, much more surprising, and much darker than what meets the eye. And today we are going to discover what modern cosmology says about the fundamental makeup, the fundamental reality of the cosmos. Our story begins in 1933 when this gentleman, Professor Zwicky, a Swiss-American astronomer who was working in California at the time, made an astonishing observation. He observed the Coma cluster of nebulae, as they were called at that time. This is a point in time when nobody was really sure what those extragalactic objects were. Nebulae, as Hubble had discovered earlier on in 1929, were objects that were further out from us than our own galaxy, the Milky Way, but nobody quite was sure yet that those were actually other galaxies in the cosmos. So Zwicky made a number of observations using a specially designed telescope, one of the biggest telescopes at that time, to map out the distribution of nebulae within a big cluster called the Coma cluster. You can see at the center of this picture Zwicky's original data. Each one of the dots on the picture is a nebula or a galaxy. They're all part of the same cluster. They're held together by gravity. And you can see on the right a modern picture of the same cluster showing these galaxies in more refined detail than Zwicky could see them. Zwicky realized that those galaxies, in order to be held together by gravity, they could not move too fast, because if their velocity was too big relative to each other, they would not have been able to stay together in the same cluster. And so based on this kind of arguments, he calculated how much gravity was necessary in order to keep the galaxy cluster together in the face of the velocities that he could observe at which those galaxies were moving. And he made an astonishing discovery, namely that in order to keep the galaxy cluster together by gravity, a large amount of unseen mass was needed. An extra source of gravity to hold the galaxy cluster together, which Zwicky could not account for because it did not show up in his telescope. Zwicky called it dunkle Materie in German, what we now call dark matter, an unseen source of gravity that must have been at work as the source of the gravitational attraction that kept the cluster together. This was almost 100 years ago now, but ever since, a great deal of other observations have confirmed Zwicky's pioneering idea that something else needed to be out there in the universe. One of the other lines of evidence for the existence of dark matter comes from the way galaxies spin around their axis. So you see here a picture of the Andromeda Galaxy, our nearest neighbor in cosmic terms, only 2.5 million light years away from us, relatively nearby. In fact, the Andromeda Galaxy is so near that it's gravitationally bound to our own Milky Way. The Andromeda Galaxy, like many other galaxies, spins on its axis, and as you move out from the center of the galaxy towards the outskirts of the galaxy, you'd expect the velocity of stars as they turn around and orbit the galaxy to decline, because further out, the gravitational attraction exerted by most of the visible mass, which is concentrated in the center of the galaxy, the bulge that you see, luminous bulge at the center of the galaxy, that gravitational force declines as you go out in the outskirts of the galaxy. So the expectation from using Newtonian mechanics, or for that matter Einstein gravity, it doesn't really matter on these scales, is that the rotational speed of galaxies should decline with distance from the center, as seen in the diagram as shown by the dashed line. However, pioneering observations made by Vera Rubin, whom you see in the bottom left in a picture taken around 1947, and then confirmed ever since by many others, the observations actually showed that in many galaxies, the spin velocity of the galaxy did not reduce with distance from the center, the solid line in the graph. The observations show that the velocity stays constant all the way out to the outskirts of the galaxy, which is a result that cannot be explained by the visible matter alone or by using Newtonian gravity. In the bottom right, you can also see another more modern observation. This is the spinning rotation of our own galaxy, the Milky Way. This is more difficult to measure because we are inside the Milky Way, so getting the handle of how exactly the Milky Way rotates is actually harder than observing the rotation of galaxies outside of the Milky Way. But you can see the data, the black points, are well explained by the green line, which, as we shall see, is a green line that contains both the gas and the stars, but also the dark matter in the galaxy. But they are not at all explained by using the red line, which is what you would expect using Newtonian gravity and only the visible content, the gas and the stars of the Milky Way. So Vera Rubin and many others, by making these kinds of observations, confirmed Zwicky's insight that if Newtonian and Einstein gravity are correct, then we need extra source of gravity in the galaxies in order to hold them together as they spin around. Another strong line of evidence in favor of dark matter. But the mystery deepened for cosmologists around the mid-90s or the end of the 90s, because at that point in time, scientists were already quite confused by the existence of dark matter, but the problems were about to get worse. There were two teams of astronomers around that time who almost at the same time simultaneously made an astonishing discovery that indeed was worthy of the Nobel Prize for Physics a few years back. And that discovery revolved on observations of a particular type of exploding star called supernova type 1a, which you see in this artist impression as the small white star in the bottom right. Now, supernova type 1a's are the explosions that happen at the end of life of a particular type of star, a white dwarf, a carbon-oxygen white dwarf, a very compact, very low luminosity, very dense star. Indeed, so dense that one spoonful of matter from a white dwarf would weigh about a ton. If those white dwarfs are found in a binary system, that's to say, if they have a companion star, in this case here, you can see it's a main sequence or a red giant star, then the gravitational attraction of the white dwarf can suck in gas from the star, and the white dwarf's mass increases over time, as you see in this artist impression. Alternatively, if a white dwarf has another white dwarf as companion, the orbit of the two stars can decline over time, and as it does so, the two stars orbit closer and closer to each other until eventually they merge in one single entity. Be as it might, in these two configurations, in these two mechanisms, what happens at the end is that the white dwarf acquires additional mass, and at some point the mass that the white dwarf accretes is so large that nothing can stop it from accreting even further. So this means that the temperature at the core of the white dwarf grows, and as the temperature grows, a thermonuclear reaction is set off in the core of the white dwarf, which in a matter of a fraction of a second destroys the star in a big explosion that generates a lot of energy, lots of neutrinos, a type of almost invisible particle, but also importantly, a great deal of light. So these supernova type 1a explosions produce very powerful beacons of light that are scattered through galaxies in the universe, which astronomers can use and did use in the 90s to measure distances to these galaxies far away from us. You can see here a supernova type 1a going off in the outskirts of a galaxy. You can see it's a bright object in the bottom left corner. This is a relatively nearby supernovae. The distant ones are much less visible, much less evident. So in order to find them, astronomers have to take lots of pictures of distant galaxies, like you see in the diagram on the right, keep coming back to the galaxy and subtract off one image from the other until what's left over is a bright dot, which is the telltale sign that perhaps a supernova explosion has gone off in that galaxy. And if that is a supernova, then following it up over a matter of a few weeks enables astronomers to determine the distance from us to the galaxy where the supernova went off. And so this procedure was carried out for about 40 or so supernovae very far away from us in the late 90s, and the two teams of astronomers, led by Adam Rees and Saul Perlmutter, discovered something quite astonishing that nobody had expected. Namely, that the galaxies in question were farther away from us than was expected under the assumption that the universe expands and is subject to gravity. As the universe expands after the Big Bang, gravity slows it down, and so whatever the universe contains, be it matter or dark matter, or even energy in the form of neutrinos or light, should slow the expansion of the universe down. But the observation of this supernovae type 1a showed that rather than declining, that slowing down, the expansion of the universe in the last 6 billion years of the life of the cosmos had been picking up speed. The universe was expanding at faster and faster speed. Something that could absolutely not be explained using the normal types of matter and energy that we know about. Not even dark matter could do that. Dark matter having gravity would have slowed down, if anything, and did slow down the expansion of the universe. Something else was needed to explain this data, and that something else we now call dark energy. So all in all, after many decades of exploration and discovery in the universe, what we are left with is a very tantalizing picture of a surprising universe, one that was unexpected and quite difficult to comprehend, certainly difficult to explain. A universe where only 5% of the contents are normal matter, the same kind of matter you and I are made of. 25%, 5 times more, is made of dark matter. And a mighty 70% is dark energy, which is responsible for the accelerated expansion of the universe today. And now, of course, the big question is, what is this 95% of the universe made of? How do we know it exists in the first place? I've outlined some of the lines of evidence, but there is much more out there that convinces us that indeed dark matter and dark energy are real, albeit invisible, conventionally invisible, and so far undetected in the lab. And therefore we need to rely on cosmology, rely on astronomy to understand those dark components, in the hope that our understanding of this dark side of the universe will unlock mysteries about the fundamental nature of reality, the fundamental nature of the universe itself. Before turning our attention to what possibly dark matter and dark energy could be made of, let's investigate a bit more the evidence in favor of their existence. After all, the claim that 95% of the universe is unknown and undiscovered is quite exceptional, and exceptional claims do need exceptional levels of evidence. The evidence for dark matter is pretty strong, and most of it comes in the form of gravitational effects that dark matter exerts on various objects in the universe at different points in the universe's history. One of the lines of evidence comes from an effect predicted by Albert Einstein with his theory of general relativity, which unified space and time into a single entity called space-time. Einstein's insight was that space-time is malleable and deformable by mass, and so the presence of massive bodies like the Sun creates a dip in the fabric of space-time, which in turn dictates how objects, or indeed light rays, move through that space-time. So if you have a beam of light which travels through the universe, as it encounters the deformation brought about by the massive presence of the Sun, its trajectory will change, or more precisely, the shortest path in a bent space-time is not a straight line. This effect leads to a phenomenon called gravitational lensing or gravitational deflection, meaning that the path of a star, for example, behind the rim of the Sun, is bent out of a straight line by the presence of the Sun, and therefore there is a difference between the actual position of the star and the apparent position of the star on the sky, which can be measured and probed during a solar eclipse, which is what Arthur Eddington did in 1919, confirming in a spectacular fashion this prediction of Einstein's general relativity. Now, the same effect can be used in cosmology to detect the presence of dark matter. It's exactly the same notion, except on much bigger scales. Now, rather than having one star behind the rim of the Sun, we have an entire galaxy far away from us, whose light travels through the cosmos and whose path is bent by the presence of a massive galaxy cluster of the type that Zwicky observed way back in 1933. And as it does so, the galaxy, with its presence, the galaxy cluster changes the path of light, and it makes it converge and deforms the aspect of the galaxy that we observe in our telescopes. Here is a picture of the Abell 2218 galaxy cluster taken by the Hubble Space Telescope. The galaxy cluster is the bunch of bright yellow, brownish galaxies in the foreground, but if you look closely, you will see a number of arclets and arcs and rings around those galaxies. Those are the shapes of distant galaxies that have been bent into arclets by gravitational deflection due to the cluster itself. Using Einstein's general relativity, we can work out how much mass is contained in total in the cluster so that we can explain the amount of bending we see. And this observation and calculation together show, again, like Zwicky determined, that the mass of the cluster needs to be much larger than the visible mass that we can see in this picture in order to explain the gravitational bending, and not a strong line of evidence in favor of the existence of dark matter. A few years back, a number of observations were then put together to investigate a phenomenon such as this, called the bullet cluster. The name comes from the obvious bullet-like shape you can see in pink in this picture. What the picture shows is the reconstruction obtained with a number of data sets of the collision between two huge galaxy clusters, which has happened a few million years ago. The two galaxy clusters have met and collided and have gone through each other. And in blue, you can see the reconstruction using gravitational lensing again of where most of the mass of the two clusters now resides. You can also see that this mass coincides with the location of the galaxies that make up each of the two clusters. But in red, an image which has been acquired using X-rays, we see the location and the position of the hot gas. The hot gas that was between the galaxies, part of the clusters, and that has been stripped away and slowed down by friction as the two galaxy clusters encountered and went through each other. So the hot gas, the normal matter that's in between the galaxies, has been slowed down by the collision due to friction, but most of the mass, the blue halos that you see, is still at the same place where it was before. It just went through one another, the two galaxy clusters, without much disruption. Another indication of the existence of dark matter and of the fact that dark matter does not interact like gas would, because otherwise it would have been slowed down, just like the pink blobs have been. And that's, again, another indication for the existence of dark matter. Perhaps the strongest indication of dark matter, though, comes from the very early universe, from the relic radiation from the Big Bang. This picture, acquired by a space telescope called Planck, shows the baby universe, that's to say our cosmos as it was 380,000 years after the Big Bang. This is a very simple universe which contains very simple components, among them hydrogen, helium, light, neutrinos, and dark matter, we believe. This universe does not contain yet galaxies. There has not been enough time to form the galaxies yet, but it contains tiny little imperfections, which you see here in red and blue, in the distribution of matter and energy. And those imperfections are the seeds out of which galaxies eventually would grow. Like Stephen Hawking once said, without imperfection, you and I would not exist. Analyzing statistically this map allows us to work out what exactly the universe contained at the moment in time, and also work out other characteristics of the cosmos, including how it began in a period called inflation, but also its current age, 13.8 billion years, and many other properties that are really important to understand how the universe works and what its fundamental makeup is. The statistical analysis of this picture leads to this kind of diagram. The details are unimportant, but the point I want to make is that we have data coming from that very beautiful and exquisitely precise picture of the baby universe, which are shown in this picture in red. We have a theoretical prediction, which is based on a model that contains dark matter, dark energy, and contains all the elements of general relativity and quantum mechanics that we know about. And you'll see that the beautiful agreement between the green line and the red dots leaves little space for doubt. There is nothing to say that we could fit this curve without dark matter and dark energy. We do need dark matter and dark energy in order to be able to fit the data with that beautiful theoretical model. Without dark matter nor dark energy, we wouldn't be able to explain the data coming from the baby universe. So if dark matter and dark energy are real, or at least insofar as we can discern from cosmological observations, what are they made of? That's a very difficult question, and one that we're still struggling with. Indeed, we need to ascertain the fundamental reality of those components before we can actually say that we've discovered them for real, for sure. We can simulate dark matter in a supercomputer. You see here a simulation of how dark matter clamps under the influence of gravity over billions of years, and that is another line of evidence for its existence. The fact that galaxies, as we see them in the sky today, could not have grown from the tiny seeds we saw in the relic radiation to the complex galaxies that we see today in the sky unless dark matter had been there to accelerate that growth. The normal matter alone doesn't have enough time to grow from tiny seeds to big galaxies in the 13.8 billion years since the beginning. So we can simulate dark matter in a computer, and we can then compare where do we think galaxies will form when dark matter is present to where actually galaxies are in the universe. And again, statistically, we can work out a good agreement between the theoretical predictions of a dark matter scenario with the actual data that we observe in the sky. Now, there are many different explanations for what dark matter might be, and some are more plausible or more interesting than others. There is one in particular, though, that I'd like to mention because it has been for a long time at the forefront of both cosmologists and particle physicists' explanations for dark matter. And the idea goes as follows. Back in the 70s, particle physicists were puzzled by a number of problems that the standard model of particle physics, which was otherwise very successful, had in explaining the makeup of the particle zoo that we see in the universe. So they invented a theoretical explanation called supersymmetry, the proposition that for every known type of particle in the universe, there ought to be another type of particle, a supersymmetric partner with slightly different properties, and in particular, a much heavier mass than the normal standard model particles. Those supersymmetric particles, it was shown, would allow particle physicists to solve the problems that the standard model of particle physics had. And at the same time, the existence of those particles made an interesting prediction. Because those particles are much heavier than normal particles, they would have been produced in great numbers at the beginning of the universe, when the temperature was high, the energy was high, there was plenty of energy around in the universe to produce them. E equals mc squared. Lots of energy. E means you could produce particles of very large mass, m. But as the universe expanded, the universe cooled down, and as it did so, the energy to produce massive particles was no longer available, and those supersymmetric massive particles decayed away. All of them, except for one. The leftover supersymmetric particle, the relic supersymmetric particle from the early universe, which under certain circumstances is neutral and massive and stable, would be a perfect candidate to explain the dark matter that we have now in the universe. What if the dark matter particle that we see at work in the universe today was simply a leftover particle from supersymmetry in the early universe? What was more, a relatively simple calculation showed that if you put in the numbers that the theory predicted, you could end up predicting the number of dark matter particles in the universe today, and that number matched beautifully the 25% that you find completely independently from cosmological observations. So in other words, here was a beautiful particle physics theory which explained away many of the mysteries of particle physics, and at the same time, in one fell swoop, would explain away dark matter in a very elegant, economical fashion. Supersymmetry was therefore one of the best explanations, perhaps still is one of the best explanations for dark matter. However, the big problem with supersymmetry is that we haven't discovered it yet. And in particular, the Large Hadron Collider at CERN failed to come up with any hint at all of the existence of supersymmetric particles, despite having been designed precisely with that target in mind. It did discover the Higgs boson, which was a major discovery, of course, but no supersymmetry so far. And therefore, the quest for supersymmetry, the quest for dark matter, continues. So how do we make progress? We have compelling evidence for the existence of dark matter and dark energy. I've only mentioned so far the fact that dark energy was discovered, or rather the accelerated expansion of the universe was discovered by looking at the distance of galaxies measured with supernova type 1a explosions. But ever since that time, more evidence for dark energy has come in. Dark energy is a bit more difficult to pin down than dark matter because, insofar as we can tell, it's perfectly smooth in the universe. It doesn't cluster. And the only way we can actually detect it and understand its properties better is by looking at the large-scale properties and expansion of the universe. Dark energy is too weak to be detected in the lab, or at least so far every attempt has failed. And certainly it's too weak to have any observable effect on the solar system or indeed on the galaxy. We need to look beyond, we need to look at the large-scale universe. And so by looking at not only the explosions that I mentioned, not only the Rayleigh radiation that I mentioned, but also looking at the distribution of galaxies in the sky and looking at the slight changes in temperature in the photons, in the particles of light coming through the universe to us from the Rayleigh radiation, astronomers and cosmologists have been able to amass higher levels of evidence in favor of the existence of dark energy, just like for dark matter. The case for dark energy is perhaps a little bit less certain than that for dark matter, but certainly we have a big part of the universe that remains unknown, like an iceberg. Most of it floats, is found below the flotation line. It's found in the depth of the dark ocean. So how do we make progress? How do we crack those dark mysteries of the cosmos? Certainly for dark matter, one way forward is to use all of the tools at our disposal, all of our observational tools, in order to attack the dark matter problem from multiple angles. We can therefore look for dark matter both in the sky, by looking at the Rayleigh radiation, the galaxies, and also other types of light coming from dark matter perhaps. But then we also want to be able to look at dark matter from a terrestrial point of view by using laboratory experiments that perhaps will be able to unlock its dark matter particle properties, if indeed dark matter is a new type of particle. Looking at the sky, for a long time, hints have been coming from a type of very highly energetic light called gamma rays. Gamma rays are exciting because they open a new window on the universe. It's a type of light that's higher energy than the visible light that we can see, and therefore it unlocks the view of phenomena that happen typically at higher energies. In particular, to do with dark matter, if two dark matter particles meet and collide, under certain scenarios they are expected to annihilate and emit in the process a bunch of high energy gamma rays that we can detect. So one way of looking for dark matter would be to look for regions in the sky where dark matter is supposed to be more dense, therefore where the chance of dark matter particles meeting, colliding, annihilating, and giving off gamma rays is higher. One such region is the galactic center, the center of our own galaxy, where the supermassive black hole lurking there amasses a great deal of matter, gas, and also dark matter all around. Unfortunately, for this kind of research, plenty of other phenomena in the universe also emit gamma rays, and therefore gamma rays are not the exclusive precinct of dark matter. You see here a picture of the whole sky taken by the Fermi Gamma Ray Telescope, showing gamma ray emission from various places, including the galactic disk, the galactic plane, which is the bright red band we see in the center of the picture. But if we zoom in into the galactic center, the bottom plot, the bottom square, shows the predictions for the gamma ray signal that one would expect from dark matter if it was lurking there. And the top zoomed in version of the data shows a pattern of emission that's tantalizingly similar, and that has led some to conclude that this is evidence for dark matter in the galactic center. Unfortunately, the evidence is difficult to interpret, and over the years there have been many claims and counterclaims that this, first of all, was a real signal, and if it was a real signal, was it really dark matter? Maybe it was due to a class of rotating stars called pulsars, or maybe something else. So the evidence is not clear-cut. There is too many confounding factors in the gamma ray sky to be quite sure that what we're seeing here is dark matter. So people have turned to underground rather than going to the sky. Perhaps we could build a detector that will find dark matter for us in a controlled environment so that we can be sure of its nature and of its properties. For many years now, the race has been on to build dark matter underground detectors able to shield all other particles, all other interactions that would perhaps give confusing signals, and just sit there quietly waiting for the rare case when a dark matter particle streaming through will hit one of the atoms in the detector and give a sign of its passage in the form of a shower of electrons and a shower of light afterwards. So these big detectors, one category of them is filled with xenon gas and liquid in order to have a very stable and very pure and very suitable target for the dark matter particles to bump into and give off the very faint signal of their passage. Here you see picture the LZ dark matter detector, which is one of the most advanced of its kind, now containing up to 10 tons of liquid xenon, which is sitting at the bottom of a mine in order to be shielded from the confounding signals coming from the atmosphere or indeed from space that would completely swamp the faint dark matter signal the experiment is looking for. So far, no dark matter has been found, but this and other detectors being built will take the sensitivity of these experiments to the ultimate limit in the hope of being able to finally discover dark matter in the lab. And so we see that astronomy goes underground in order to be shielded from the signals that would swamp the dark matter whisper. And so there's a new breed of astronomers who actually, rather than going up to peaks at the top of mountains to big telescopes, they go at the bottom of mines, kilometers underground in order to do their job. And if you want to know a bit more about this, one particular site, the Bowlby mine in Yorkshire, which has hosted one of the previous versions of the LZ experiment, I highly recommend the beautiful book by Robert Macfarlane, Underland, which explores all sorts of underworldly environments, as the title implies, but particularly one chapter explores the dark matter research that goes on at Bowlby, and it's beautifully written and really, really enticing. One aspect that I'd like to mention is that in the quest for dark matter, physicists are pushing technology to its limits. And one of the limits is that we need to be able to shield our detectors from every other signal in order to make it as quiet as possible inside the detector. And one of the signals that might be masking the dark matter comes from the detector itself and the layers of shielding around the detector. In particular, lead is a very good shield, preventing other particles and rays to intrude into the detector, but not if lead itself is radioactive. And normal lead is naturally radioactive to a very low level, but high enough, nevertheless, to make to disturb the signals that physicists are trying to detect with dark matter detectors. So particle physicists have been looking for lead that was not radioactive, and one of the best sources of such lead is wrecks of Roman ships, where an ancient lead that spent the last couple of thousand years underwater has been depleted of its radioactive content, was not reactivated by cosmic rays, which have been shielded by several meters of water. And therefore, it's a very good source of shielding for dark matter detectors. And so in a sense, it's beautiful to see ancient technology in the form of ancient lead pipes or lead lingots being used for the one of the most technologically and scientifically advanced endeavors of today, dark matter research. On the other hand, this also throws up all sorts of ethical questions, because lead, ancient lead, recovered lead, has to be seen as a finite resource, and one that is also precious from a point of view of archaeological inheritance, and certainly archaeology and conservationists have been making the case that we need to be careful to use this lead properly, only for the applications for which no alternative exists, and dark matter research perhaps is one of them. Another way of discovering hopefully dark matter or hints of dark matter's nature is at the Large Hadron Collider, which is now undergoing a refurbishment which will increase its energy and its luminosity, that's to say how many particle collisions happen per minute, manifolds when it comes back online. And so in the next decade or so, there's every hope that the new Large Hadron Collider will be able to increase its energy to a point where it might see finally hints of supersymmetry, and from there perhaps hints of dark matter. Dark energy remains more mysterious, and it's so mysterious, in fact, that we really are puzzled by its very existence, and are puzzled even by the fact that its value, while apparently important in the makeup of the universe today, 70%, is actually much smaller than one would expect from quantum mechanics. If we take our best theories of quantum mechanics, of the particle physics world, and we try and make a prediction for how much dark energy there should be in the universe, one comes out with a number that's 120 orders of magnitude bigger than the number you need to explain the dark energy that astronomers see in the universe. This mystery goes back to Einstein, in fact, who in 1915, when he devised his theory of general relativity, realized that the universe would expand under his theory, and he wasn't prepared to accept this fact, because he thought at the time the universe to be static, never changing with time, out of philosophical and metaphysical grounds. So what Einstein did at the time was to tweak his equations, introducing an extra term, an extra number in the equations that he had previously set to 0, and called that the cosmological constant. The cosmological constant in Einstein's vision of the universe was there to stabilize it against expansion. So the universe would not expand, would not contract, would just stand there static, unchanging for all times. However, that universe was unstable, just like you can put a pencil on its tip. If you are very careful, you can make it balance there, but if you move it ever so slightly, it will fall either way. So was Einstein's universe unstable. perfectly balanced cosmological constant could prevent it from expanding or contracting, but the slightest perturbation would make it either crash upon itself or expand forever. Later on, when Hubble discovered in 1929 that the universe is in fact expanding, Einstein realized his mistake and reportedly called it his greatest blunder. However, history then shows that perhaps Einstein was right after all, because the dark energy we've been talking about indeed has all the characteristics that Einstein gave to the cosmological constant. So Einstein was perhaps right after all, and the cosmological constant does exist in the universe today. In order to make sense of that, we will need better data, new data that will enable us to measure the expansion of the universe with even finer precision, to establish whether the universe has been expanding at a fast and ever accelerating rate in a uniform fashion for the past 6 billion years, in order to pin down the characteristics of dark energy and make progress on its actual fundamental nature. So one way to do that will be with the Vera Rubin Observatory, a new telescope, an 8.4 diameter telescope that will come online in the next couple of years and will enable astronomers to image the entire sky every 3 nights, delivering a great deal of data about the position of up to 37 billion stars and galaxies in the universe, which will map out both dark matter and dark energy to unprecedented precision. So in the next decade, I expect every corner of the dark universe to be scrutinized to even finer accuracy, in the hope of pinning down the nature of dark matter through observations of the sky, through listening into the whispers of dark matter coming through detectors underground, through the production of supersymmetric particles at the Large Hadron Collider, and also through the observation of galaxies and exploding stars in the remotest parts of the universe, in order to find out whether dark energy really exists, and if it does, what is its fundamental nature. So I have little doubt that the next decade will be a great decade of great discoveries for cosmology, and in 10 years' time we will have made great progress in understanding the dark side of the universe.